بسم الله الرحمن الرحيم والصلاة والسلام على أشرف المرسلين سيدنا محمد وعلى آله وصحبه أجمعين. Welcome back, everyone. In this first tutorial, we will take the tools that we've learned so far, and we're going to apply them to simulate our tooling manipulator. However, we will not be simulating the symbolic mass matrix and covariance interpreted matrix and gravity vectors. We could. However, we will be doing this using the Robotic Systems Toolbox. Okay, so the Robotic System Toolbox from MATLAB. It's actually it does not implement the dynamic equations of a manipulator using symbolically, but it actually does it numerically, and it works very efficiently for higher dimensional systems. So actually, you can check for out this link, and you can see here that we actually it implements a lot of interesting stuff, much more than just the modeling. It actually also has some path planning and collision checking and trajectory generation and much more. Okay, so you can check here out the tutorial yourself. What we need to do here is that we need to first design our robot. We need to build our robot using this robotic system toolbox, and actually it requires all of the body fixed frames to be placed at the joints. So not what we did in tutorial number 2, but actually what we did in tutorial number 3, when we placed frame number 1 and frame number 2 at the joints and not at the center of mass. So all what you need to specify from what we learned before for the robotic system toolbox is the mass of link I. So where I here is from 1 to n, depending on your manipulator. Here we had a 2-link manipulator, so I is from I equal to 1 and I equal to 2. So we provide the mass of link I, the moment of inertia of link I expressed in the joint frame, not in the center of mass, but in the joint frame. The location of the center of mass expressed in each frame I, in the joint frame. And also the robotic system toolbox expects you to define the pose of the joint frame in the home configuration with respect to the parent frame. So it wants to see frame I with respect to frame I minus 1. So the pose of frame I with respect to frame I minus 1 in the home configuration. So it wants 1 with respect to 0, 2 with respect to 1, and E with respect to 2, and so on and so forth. This is usually how it works. And what we used earlier to actually to define them, we actually defined I with respect to 0. However, it's not that hard to actually just use this formula and you can get I with respect to I minus 1. So it's actually trivial from what we did before. So now let's start. Let's run as usual the first stuff that we do, which is just loading the packages and our helper files. We also need to look tutorial number 3. We'll be doing. We already implemented. We already defined, for example, the inertia and the location of the center of mass there. We'll see how we're going to be using them. And also what we're going to be doing in this tutorial is that we're going to be comparing the numerical matrices that we get from the robotic system toolbox to the symbolic ones that we derived last tutorial. The first thing that we will do is that we will be substituting all of the, we're going to be defining numerical values. And we already, last tutorial, we defined some of the actually all of the stuff that we had symbolically. So we will need to substitute all of the symbolic symbols that we had with numerical values. And we're going to be defining this parameter structure, parameters, and inside of it, it will have a number of fields, L1, L2, M1, M2, and so on and so forth. And this is a special function that will allow us to, for all of the symbolic independent parameters of the moment of inertia, we will identify the numerical values that you see here in this array. So this is a specially made function to do that. And we also have the gravity here. And if you want, we can actually check what's inside of this parameters vector, what's inside the parameter structure. And inside here, it actually say we have a struct with the fields L1 that has a value of 0.5, L2 with 0.3, and so on and so forth. So this is what we build here in these lines of code. The robotic system toolbox, beware that it does not allow you to do any symbolic computations. It only works numerically. Okay. So now what we do here is that we will actually replace all of the parameters that all of the symbolic parameters that we did earlier with the numerical values. So actually, what this struct does, actually, it's a function that it's part of our course helper functions. What it does is actually it just substitutes for the symbolic variables in an expression with the numerical values that are available in the structure that we provide. Okay, so that's exactly what we do in this line. So we defined in tutorial number 3 the center of mass location in frame 1, and now we just get them afterwards in numbers. The same for the generalized inertia. We have them in numbers now. We have the location of the second center of mass in frame 2, second moment of inertia, and so on and so forth. Even the home poses for the frames we have them in. And as I mentioned earlier, we need to define each link with respect to its parent. So 1 with respect to 0, 2 with respect to 1, and so on and so forth. And that's why we do this computation here. So what you see in this line is actually what we had in this expression. Okay. So that's it. So this is all of the preparation that we need to do from what we did from tutorial number 3. And now we can build our robot. The main object in the robotics system toolbox is what's known as a rigid body tree. Okay, so we build it like that. And then we start to add bodies inside of this tree. And all of these bodies will be connected together using joints. So the first body we're going to be calling it link number 1. And we're going to be defining joint 1. We're going to call it joint 1. So that's the name of the joint. And it's a type of a revolute joint. We did not specify here the axis, and by default, the axis will always be 0, 0, and 1. So if you do not specify it here, it assumes that you want to rotate around the z-axis, and that already matches with how we define our robot here. So because we have that, actually this is a planar robot, and the z-axis is always outside of the screen here, and this is actually the same axis of revolution, the positive axis of revolution for all of our joints. So this is how we defined the joint, and then we say that we want to transform the joint. We want to transform it by this pose at the home configuration. So this is frame 1 with respect to 0. So you see here we have frame 1 with respect to 0, and this is how we define them in the home configuration. This is not the home configuration. The home configuration, we defined it in last tutorial. You can check that out. But it was the downward pose of the robot. And then afterwards, we specify that we want body 1 to have the joint that is given by joint 1 that we defined above. Then afterwards, we say that body 1 has a mass, which is given by parameters that m1. So here, it will just choose the m1 value, which is just 1 kilogram. And body 1 has also a center of mass given by this vector. Body 1 has an inertia that's given by this vector. What the inertia field here of body 1 is expected, it's expecting it to use this format. So xx, y, z, z, and then yz, xz, and xy. And if you actually, remember from tutorial number 3, this is actually a little bit slightly different from how we defined the order. So when we defined the vector of the moment of inertia, we defined it x, y, y, z, z, and then we had x, y, x, z, and y, z. Okay, so if you compare these two together, you'll find there's just a different order here, and you need to respect that format. This is just what the toolbox expects you to provide. And then afterwards, so this is all of what we need to actually define for a link. Okay, that's all what we need to do, just the inertial parameters, and simply what's the body fixed frame. Okay, and it's placed at the joint, and what's the type of the joint, and how we call the body, and how we call the joint. That's it. We can similarly do the same also for link number 2. We have these two lines, which are add visual for body 1 and add visual for body 2. This is something only for us to see the robot, to visualize it. So you can do it in different ways. The robotics system toolbox, it has built in some primitive shapes. If you want, you can actually visualize the robot as simply the first link of the robot simply to be a box, and we'll be simply choosing this box to have a length of L1, so the same L1 that we the parameter that we actually defined, and it will have a thickness of 0.05 and a height of 0.05 because it defines it as a 3D box. And it's transformed such that it's shifted so that it's centered around along the link. So exactly it's centered at L/2. So this is usually how we define the visualization of the first link, and this is how we do the visualization of the second link. You can use you can do more complicated stuff if you want. You can actually visualize the link 1 and link 2 using CAD files, and you can even do it in more fancier ways if you want. Afterwards, so what we did so far, so now let's just recap. We already defined frame number 1 and we attach it to link 1, and we already defined frame 2 and we attach it to link 2. Now what we want to do is actually we want to define frame of the end effector. And to do that, the Robotics System Toolbox does not allow you to add fixed frames. It only allows to add rigid bodies. So what we're going to be doing, the workaround is that we're going to be adding a rigid body. We're going to be calling it the tip of the robot. And we're going to be attaching it using a fixed joint to link number 2. And we're going to be transforming it simply by a translation. So it will be equivalent to the frame 2, but just translated by L2 in the X direction. If you look at here, these two frames, they're actually exactly the same. They're just translated along the X axis of frame 2 with a distance of L2. So this is how we define here. And then we're going to be saying, okay, that with this body that we defined has a joint that's given by this fixed joint that we defined. And it has a mass of 0 and an inertia of zeros. And in this way, this rigid body actually is just, it doesn't exist and does not change at all the mass matrix. And the Robotics System Toolbox will actually neglect it. It will not consider that actually you have a 3-link robot. But this is the way that you can actually add another body fixed frame to join to link 2. So now we have frame 1 attached to link 1 and frame 2 and frame E both attached to link 2. So this is usually the standard way of how you can add just a frame to your robot. And then afterwards, now we have the 3 bodies, body 1 and body 2 and the end effector body that we just defined. And we're going to add them each. We're going to add each body to the robot. So actually to our robot here was this rigid body 3. So we add inside of this robot body 1 and we attach it to the base. So this is like the fixed base of the robot. And then we attach body 2 to link 1 and the end effector body to link 2. Okay, so we do this rigid body 3. In this way, we define that the direction of gravity will be in the minus y direction with respect to the 0 frame. And there are more tutorials online of how you can build this rigid body 3 in step by step and more features. That's it. So you see here our 2-link manipulator with this extra frame is simply just these simple pieces of code. And then now let's run them. And the Robotics System Toolbox, it gives you a lot of extra functionalities that you can analyze and you can do more with your robot after you build it. The first thing that we're going to be doing is use the show details function. The show details function actually just showed us all of the details of our robot. You see we have index 1 and 2 and 3 for link 1, link 2, and for the tip. Remember that link 1 was the name of the first body, link 2 was the name of the second body, and tip was the name of the end effector body, this imaginary body that we added. And it's the joint name for the first of the one that has the first index is called joint 1, joint 2, and then the tip fix. This is the names that we chose. We chose the first 2 joints to be a revolute and the third one to be a fixed joint. Okay. And then we have base, the parent of body 1, which is the link 1 is the base. The parent of link 2 is link 1. The parent of the tip body is link 2. And also you can see here the children for every link that we have. So this is okay. This after you build your robot, you must always use the show details to actually check whether you build the robot correct and if there are any mismatches from what you intended to do. So that's it. So now we build the robot. We can start to play around with it. What we're going to be doing now is that we're going to actually show the robot. So there is another functionality here that we can show the robot. So actually, we run this block. You'll see that this is our robot that we visualized. And to visualize your robot, you need to specify which configuration that you want to visualize it in. So the configuration is given by the joint angle. So this is the joint angles live in the joint space, and this is the configuration space of the robot. So if we specify an angle for joint 1 and another angle for joint 2, we already have all of the information we need to describe the robot. And you can change this. So this is in radians. So let's say, for example, we want to choose pi over 2 for the first angle and 0 for the second one. So this is our robot. This is how it looks like. We do pi over 2 and pi over 2. Okay. And we visualize it. Okay, we see the robot looks like that, and so on and so forth. Okay, so you can play around as you wish with your robot. And also you can just for fun, that's just run the robot for random configurations. Okay, now we just every time we run this piece of code, we just get different configurations randomly for Q1 and Q2. Okay, so you see here, this is how our robot looks like. And you see here the two boxes here were actually how we visualize it. How we build the robot. If you want to change the visualization of the robot, you can actually play around with these parameters. For example, if we do this 0.25 and actually 0.25 is too much. Let's make this, for example, 0.1 and give this 0.05 as is. Let's rebuild the robot and visualize it again. You see actually our visualization of the robot changed now. Okay, so our first link is much wider than the second link. So this is just for visualization purposes. Does not at all change the dynamics, because the dynamics is only specified by the inertial parameters and the transformations, which are independent here from the visualization. Okay, so you can do here whatever you want, because this is just how you visualize the robot. But this is what specifies all of the information here is what specifies the dynamics and how the robot will move with time. Okay, so let's go back to our first design of the robot. Now visualize it again. You see, okay, so this is our robot now. In the remaining of this tutorial, what we're going to be doing now is that we're going to be comparing what we did in building this robot in tutorial number 4 and what we did in tutorial number 3. If you remember, in tutorial number 3, we already computed the forward kinematics, we computed the differential kinematics, we computed all of the dynamic matrices using the Lie group approach, using the product exponential and geometric Jacobian and so on. So we already computed all of this matrices, and we want to see whether we're going to be getting the same values as using the Robotics System Toolbox. And what are the functions of the Robotics System Toolbox that gives you the same information from what we built earlier. So let's start with the forward kinematics. Remember, the forward kinematic is simply the pose of the end effector with respect to the base. And here, this is the HE with respect to 0. This is how it looked like. So this was what we derived earlier in tutorial number 3. And if we substitute here this with the parameters, and we also substitute with Q1 and Q2 with their numerical values, you see, for example, we get something that looks like this. So this is the numerics of what we of the H matrix that we so the homogeneous transformation matrix of the end effector with respect to the base that we computed. And if you want to get the same piece of information using the Robotics System Toolbox, you can use what's the function called get transform. So the get transform, you give it the robot, you give it the configuration of the robot, and you tell it, I want this frame with respect to that frame. So we want here the frame of the tip with respect to the frame of the base. So this was the end effector frame, and this was the 0 frame. And to do that, you see here, we should get the same numerical values. Okay, and of course we can try. Maybe this was lucky shot. You can try different configurations. You see, okay, every time we can get the same value. Okay, so this is how you can get a transformation. You can actually specify here any two links. So if I want, for example, link 2 with respect to link 1, or link 1 with respect to link 2, or the tip with respect to link 1, and so on and so forth, you can always do that. So here, for example, if you want the H2 with respect to 0, you can simply do link 2 with respect to the base, and you can also compare it to what we computed earlier. And you'll see we do get all of these matrices correct. So that's it. So that's for the first part, for the forward kinematics. For the mass matrix, we already computed also symbolically. So this is, if you remember, this is how it looked like in tutorial number 3. And now we can also substitute it by the parameter. So what this actually part will do is that it will look at this symbolic mass matrix, and you'll find that we had L1 and all of the moment of inertia, and M2 and so on, and L1 and L2 and so on. So it has a lot of these parameters. When we substitute it here, what we actually get is that we get just numbers. So we get numbers, but instead of L1 and L2 and all of the parameters, But Q1 and Q2, they still remain symbolic. And afterwards, we substitute again for Q1 and Q2 with their numerical values. And after that, we get a numerical mass matrix. So this is the math matrix that we have numerically. And this is how you can get the same matrix using the robotic system toolbox by simply using what's known as the mass matrix. So you tell the mass matrix, I have this robot and I have this configuration, tell me what the mass matrix is. And as I mentioned earlier, the robotic system toolbox actually does not use the symbolic computation. It computes the mass matrix using a numerical method, and it's actually much more efficient than and memory friendly than computing the symbolic computation and symbolic matrix and then substituting it with numbers. Okay, so that's in a much smarter way. And again, let's try, for example, different configuration. Let's see whether we get another mass matrix, and yes, they always match. They should. Same also for the gravity torque. You can see, okay, the same drill. So this is how we can get the gravity torque using the robotic system toolbox. And this is the gravity torque that we computed earlier, and we just substituted with the numerical values. So far, so good. So that's actually very easy. To the forward kinematic is already implemented here. The mass matrix is already implemented here, and the gravity torque is already implemented here. The last thing that's remaining is the geometric Jacobian. The geometric Jacobian is a little bit not complicated. It's not as straightforward as from the gravity as from what we discussed so far. And the main reason is that actually it's not even clear to me why they implemented it this way. But there's actually a function called geometric Jacobian. You can give it the robot. You can tell it, I want the geometric Jacobian of this body. So here, for example, we're talking about the tip, the end effector frame, and it computes for you the geometric Jacobian. However, it expresses this geometric Jacobian not in the end effector frame, not in frame of the base, but in a third frame. So not in the frame E, but in what's known as what I call here in the figure frame E bar. So frame E bar, if you look at here, this is actually the dashed frame here. So it's actually this one. So these two frames, so actually X E hat and Y E hat, these two frames, so these two directions, they make up frame E, while X E bar, so X hat E bar and Y hat E bar, they make up this other frame called E bar. And if you see here, this frame E bar, it's actually located at the tip of the robot, located at it has the same origin as the frame E, but it does not have the same orientation of it. It rather has the orientation of the base. So this is how they implement it. Okay, and it's very weird, and it took some time to get my head around it. But in the end, this is how they implement it. Okay? And you can check for yourself. Okay, so now what we're going to be doing is the following. Let's use the geometric Jacobian and compute this the Jacobian using this function. And now let's take the end effector frame. So the end effector Jacobian of expressed in the end effector frame. So what we call the body Jacobian of the end effector. Now let's substitute it with numbers and let's see what we get. If you compare these two matrices, what you get from this function, what you get from substituting this JE, you'll find that actually they're not the same. We don't get the same matrix. And actually, this actually, as I mentioned, this is actually correct. So just so that you know that this actually is the true end effector Jacobian and expressed in the end effector frame. However, the problem actually is in this geometric Jacobian function because it's giving us in the E bar frame, not in the E frame. And to fix that, it's very easy. We already have the transformation. So it's simply we can just do a joint transformation from E bar to E. And these simple lines of code will actually do that for us. If you can check here, what we do afterwards, what we get is that we get this expression. And now if you compare this expression to this one, you see actually it's correct because they do match. Which means actually that we already fixed this issue with this geometric Jacobian. And we can actually combine this line of code with these three, and we already did that in in this function called the get body Jacobian. And you can apply it here for any link. You can give it link 1, link 2, and or the tip, and it will always calculate the proper Jacobian for you, expressed in the links frame. properly. And you can compare it to what we computed earlier and find it matches. These body Jacobians, they are very important. Okay, you'll see later they are very important for control or for getting the effect of, for example, or to studying analyzing the manipulability of the robot and so on and so forth. You can do a lot with it. So it's very important to get it right. So that's it. So that's the end of the tutorial. And this concludes what I want to show you. There's only one part that's left, and it's optional. You can actually, with your robot, you can do a lot with. You can how to say it, the user. We've been only interacting it here with our robot using these pieces of code, but you can actually build a whole GUI. You can build the user interface to actually interact with the robot that you built. So what we can do here in this line, we can actually take the robot that we built and just save it. Let's call it my robot or my 2R Planar robot or something like that. So let's save it, and you can actually later on you can build the GUI for that. MATLAB has very nice features to actually build the GUI. This is one of the GUIs that actually I built to play around with my robot. So this is the two-link robot that you see here, and this is its workspace. So this is the Cartesian space of where the robot lives. And this is what you see here on the top right corner. This is the joint space, Q1 and Q2. If you change here, for example, with these sliders, I can change Q1, I can change Q2, and you see here the robot just automatically updates its visualization. Regarding the visualization I mentioned earlier, you can actually turn them on or off. Okay, so if I want, I can just see the frame. So you can see actually we have here our frames of the robot. So actually this is frame 1, this is frame 2, and this is the tip of the robot, while the black frame here, this is just the base. So it's the fixed base of the robot. We can also, if you want, you can just remove the joint frames and just look at the visuals. You can do both. All of the points here you see actually from how the robot is actually built. We cannot reach anywhere in space, and that makes sense. The robot has some limitations, and this is actually known as the reachable workspace of the robot. And you can compute it, by the way, and you can see, for example, all of these blue dots here I visualize with the reachable workspace. Any point here that's inside of this, any point that's here that's marked in this region, actually the robot's tip, the robot's end effector can reach. Okay, so you see here, I can reach all of these points inside. However, any point that's outside of it, for example, this white area or even this white region, I can never reach it. Okay, so even if I rotate, I can try so hard to get inside, you can never reach it. Okay, this inside area. So this is usually known as the reachable workspace. You can visualize it if you want. And not only that, we can also simulate our robot. So far we've only played around with the specifying the configuration, but we already have the dynamic equation, so we can compute with it. We can compute the second derivative of the joint angles, and then we can integrate in time. That's exactly what we do here with the start animation. So let's, for example, try to simulate our robot for 3 seconds. Now if you do start animation, we had the effect of gravity, and gravity just keeps on pulling our robot, and then it just does like that. Okay, and okay, just it's simulating the equations of motion. This is, of course, a simulation that's computed using the Robotics System Toolbox, not our symbolic matrices. The last thing I want to show you here is actually, if you look at the joint space here on the top right, you'll find actually something weird. That actually this was the starting point, and you see this dashed line is what like the trace of the history of the joint. So it actually started like this, and then it started to move in this direction, and then at some point it just disappeared from here. It appeared down there, then it just kept moving, in this direction, and this is the configuration where it is right now. Okay, if you want, you can repeat the same simulation again. You'll find that, okay, for example, you see, let's repeat it again and see that's exactly what's going on. It's just going up. Then at some point it just disappears, and it seems like there's some discontinuity in the joint space. However, there's just the configuration space is actually it's continuous. We don't have any discontinuities in it, and this is just one of the artifacts of representing, the configuration space in this way, but simply as a piece of paper or an R2 as a plane. So here we assume that this horizontal plane is Q1 and the vertical plane is Q2. But this is one of the artifacts of of using charts. This is actually a chart for the configuration manifold, and the true configuration space actually does not have a Euclidean structure. It actually has a manifold structure. It's a 2D manifold given by this torus that you see here. And if we actually simulate our robot in this direction, you see that we don't have any discontinuities here. Just we're moving along the surface of this torus. The torus is just the shape of a donut, and you see we're just moving along this this surface, and we don't have any discontinuities. Okay, it's just that just it's an artifact of using coordinates, of using Euclidean representation. So that's it. You have the code of this GUI. You can take a look at it at your own pace. You can play around with it. Feel free to change stuff and play around and try to modify it as you wish. That's it. That's the end of this tutorial.